We are going to look at an introduction to acids and bases in this video. We'll go through some of the vocab and some of the main ideas here associated with acids and bases. A little bit more about acids and bases before we go forward. Acids typically have a sour taste. This is why they're used in a lot of candies, sour candies, especially here. Acids will turn litmus paper red, and they have a low pH. So a lower pH is going to be an acid here. You know, acids are found in many foods, like lemons, for example. Bases have a bitter taste. These are going to be things like baking soda and a lot of soaps. Obviously, you wouldn't want to be tasting the soaps. Bases turn litmus paper blue, and bases are higher on the pH scale. There are some different ways to define acids and bases, and some of them work in some situations, and others kind of work as a good general overview here. So the Arrhenius definition of an acid and base are this. An acid is anything that donates a hydrogen ion or an H plus in water. And then a base would donate a hydroxide ion, OH minus in water. Right? So that's the easiest way to think about an acid or a base. But the problem with this, and this can't kind of be the end-all be-all definition of acids and bases, because there's a problem here. If a substance doesn't have those parts, the H plus or the OH minus, they could still be an acid or a base. Think about NH3. NH3 is a base, but it doesn't have the OH minus in it. Okay, so we have to kind of further refine our definition here, but these definitions of acid and base work really well in most situations. If you kind of have this, general idea that an acid is going to give off an H plus and a base is going to give off an OH minus, it can be very helpful here in problems. Just realize this doesn't work for all of them, and we have to kind of go a little bit further here. So you're more than welcome to kind of have these definitions in your head. Like I said, they do work most of the time, but you have to be aware that it's kind of not the end-all be-all here. We can get a little more specific here with our definition by using the Bronsted-Lowry definition of an acid or a base. For a Bronsted-Lowry acid, this would donate a proton in water. Okay, remember an H plus has one proton, so it's kind of the same thing here. So an acid donates a proton, and a base would accept a proton here. So basically, this is a better definition for NH3. NH3 is a base. It doesn't have OH minus to be able to say it's going to donate an OH minus. But what happens is it accepts a proton. It accepts an H plus here and becomes NH4 plus, which then gives off the OH minus here from the water. So you have to think about it in terms of the base kind of accepting an H plus. That's kind of the way you think about it in terms of Bronsted-Lowry. Again, you're more than welcome to think of it in terms of, acids donate an H plus, bases donate an OH minus, but understand that you might need to think about it a little differently here for some of them. All right, so this is a better definition here. Now we can explain why NH3 is a base, because it's going to accept the proton, it's going to accept the H plus here in water. We can now use the Lewis definition here to explain all traditional acids and bases. So according to the Lewis definition of an acid and a base, an acid would accept an electron pair, all right, and a base would donate an electron pair here, all right. Do I think you're going to think about all acids and bases in this way? Probably not, because the Arrhenius definition is probably the one that is easiest to remember, makes the most sense. But you need to realize here there are other definitions, and you might have to use these and identify acids or bases in this way. But again, you might be able to use the Arrhenius or the Bronsted-Lowry definitions here to help you. But this is kind of the more traditional definition of an acid and a base. Let's talk a little bit more about this H plus ion, because we said, a traditional acid is going to give off an H plus ion in water. Basically, it's just like a proton. because in the nucleus because it has no valence electrons here. Essentially, it lost its valence electron. So H plus is going to react strongly with the lone pairs of electrons around the oxygen atom in water. So you can get forming here H3O plus. We call this the hydronium ion, which basically is when H plus reacts with water. All right, so you can kind of see that happening here in the picture, and H plus will react here with these lone pairs of electrons around the oxygen, forming H3O plus. It's the same thing as H plus. All right, so if you see H plus or H3O plus, you have to look at this as being H plus here. Sometimes in these problems, you might just see H plus written. Sometimes you might see H3O plus written. They're basically interchangeable here. It's going to be acidic. It's the H plus ion. So just be aware of that. Amphiprotic or amphoteric are molecules that can act as either acids or bases here. All right. Amphiprotic basically means it's capable of accepting or donating a proton here. All right. So for water, water is amphiprotic or amphoteric. Water can act as an acid or a base. So if water's acting as an acid, it can give up one of its hydrogen atoms here, okay, essentially donating an H plus, donating a proton here, or water can act as a base when it accepts the H plus or it accepts the proton here. So water is what we call amphoteric. It can act as either an acid or a base. So just be aware of this vocab in case you see it. There are certain substances that can, act as an acid and donate an H plus, or they can act as a base by accepting that H plus. Now we want to talk about conjugate acid-base pairs. All right, these would be pairs of compounds that differ by the presence of one H plus unit here. All right, you definitely need to be able to identify conjugate acid-base pairs here in reactions. So for example, we have this compound in this reaction is an acid. It starts with H, all right, it's going to be an acid. Well, when it's in equilibrium with its ions, all right, it's essentially going to give off an H plus here, and then the A minus would be your conjugate base. All right, it's differing only by the presence or absence of this H plus. This would be the acid, and then this would be kind of the opposite of that, or the conjugate base here. You can add the H plus to this to make the conjugate acid. All right, so if you were going in reverse, the A minus would accept the H plus, so that would be your base. That's the definition of a base. And it would form HA, which would be your conjugate acid here. So you need to be really good with this, be able to look at a reaction and identify the acid and the conjugate base and the base and the conjugate acid. So for example, if we're looking at this reaction here in this picture, right, this substance here with the H on the end would be the acid. So when it loses that H, all right, and forms the CH3COO minus, that would be the conjugate base here. All right. Then on the other side, this would be the acid, and when it loses that H plus, this would be the conjugate base here, or this would be the base if we're going forward, all right, because it can accept an H plus, and this would be the conjugate acid here. All right, so you're definitely going to need to be able to look at a reaction, pick out the acid base, pick out the conjugate here. And really the only difference is, you're like losing or gaining an H plus pretty much for most of these examples. The basic gist here of these conjugate acid-base pairs, if you want to get a conjugate base of an acid, just remove an H plus, all right? But don't forget the minus sign here. If you're removing an H plus, what's left now is going to be minus, all right? So that's kind of very important here. So if we have an acid, for example, here in this equation, the water, all right, you want to remove the H plus there, and that's going to give OH minus, and that would be the conjugate base here of that acid. If you want to get the conjugate acid of a base, just add an H plus, but now remember you're adding an H plus, so you're going to have a positive sign here. So if we look at this example, the NH3 is going to be the base. If you want to get the conjugate acid, just add an H plus to him. All right, he becomes NH4 plus. All right, so think about it in terms of either removing an H plus or adding an H plus here, but you definitely need to be able to do this. If you want the conjugate base of an acid, pull off an H plus, all right? If you want the conjugate acid of a base, add the H plus. Let's do a little practice here. We want to write the conjugate base for each of the following acids. Now realize here, some of these might not be traditional acids in the sense they may not necessarily, really want to give up the H plus or anything like that. But this is just some practice here to get you used to doing this. So if we look at the first one, we have CH3, CH2, OH. Now traditionally this is not going to be an acid, but we'll just pretend like it is. We want to write the conjugate base of this, right? So we know it's an acid. To write the conjugate base, you're just going to pull off an H plus, all right? But when you do that, you're going to end up with a molecule that is minus now. So when we remove an H plus here, I'm going to remove this end one, all right? We would get CH3, CH2O minus, all right? So if you want to form the conjugate base of an acid, pull off the H plus, just watch your charge. So what I would do now is pause the video, work on the last four, and when you rejoin, you'll see the answers already there. Make sure you can do this. So pause the video right now. Okay, hopefully these are the answers you got here. Remember, in order to write the conjugate base for all of these acids, you need to remove an H plus for each and watch the charge. So for H3O plus, if you remove an H plus, now you just have two H's, but you lost a plus. So it's just H2O. For the next one, you're pulling off an H plus. So now it's just HPO4, but now you pulled off another plus. So now it's going to be 2 minus instead of 1 minus. NH4 plus becomes just NH3. And then HCO3 minus, you lose another hydrogen. So it's CO3 2 minus because you lost the plus here. All right, so just remember, anytime you want to make the conjugate base from an acid, pull off an H plus and watch the charge. Now let's try to write here the conjugate acid for each of these bases. Remember, if we want to write a conjugate acid, we need to add an H plus to all of these. Just be careful here of the charge. So let's do the first one here, the NH2 minus. We want to write a conjugate acid for this, so we need to add an H plus. So when we do that, we're going to have NH3 now, but we added a plus, which would cancel out the minus, so it's just NH3. There's no charge on this, all right? So again, add an H plus to all of these to get the conjugate acid and watch the charge. I would pause the video right now, make sure you can do the remaining four, and when you rejoin, I'll have them solved for you. So pause the video and try it. Hopefully, these are the answers you got. Remember, we're adding an H plus to all of these. All right, so you just got to be careful there of the overall charge. For example, for this OH minus, when you add an H plus, now you're going to have H2O, but the plus and the minus cancel each other out. So it's just H2O with no charge. And you can see the rest here, but this is what you need to be able to do to form a conjugate acid from any base. Add an H plus and watch the charge. For this example, we want to identify the acid on the left and its conjugate base on the right, and then we'll identify the base on the left and its conjugate acid on the right. So basically, you're just going to try to identify the acid and the base on the left first. And you can use those definitions of acid and base. So in my head, I know the general definition of an acid is it has an H plus to kind of give off, and then the base would be accepting that H plus. So you might have to look at your products here and see what's going on. They both have H's in them, but I can see the HBr here is losing the H plus to form the Br minus on the right. So that one is going to be the acid here. Okay, so the acid is going to give up the H plus, so that would make the Br minus the conjugate base of that acid because it lost the H plus. That must mean the NH3 is going to be the base on the left, and it's going to gain an H plus, all right, on the right side. So that would make the NH4 plus the conjugate acid here. So you just got to be careful of your definitions. The conjugate acid is going to gain the H plus. The conjugate base is going to lose the H plus. All right, so you definitely need to be able to identify the conjugate acid base pairs in any reaction here. Now we want to look at the strengths of acids and bases here. Some acids and bases are what we call strong, and others are weak. And we need to be able to identify them, and different things happen with these strong acids and bases compared to the weak acids and bases. Strong acids and bases dissociate completely in water. That's a big thing to understand here. What that means is they ionize or turn into the plus and minus, all right, they're ions 100%. All right, if you have an acid that is considered strong, it dissociates completely in water. We are not talking about concentration here. That is not what this is. This is just literally identifying an acid or a base as strong or weak. A strong acid dissociates completely in water. It turns into its ions 100%. There's none of the original acid there, essentially. All right, so these strong acids and bases have very large K values. Essentially, they form all of the products, if you will. If you think about your K value for your equilibrium constant, it'd be products over reactants. If you have a very large K value, you have a lot more products here. Essentially, when we're looking at strong acids and bases, we don't show equilibrium with them because they're 100% forming the ions here. They're dissociating into the ions 100%. So if you have a beaker of HCl, all right, it's important to understand that there's no actual HCl molecules in that beaker. There would just be H plus molecules and Cl minus ions. Okay, there'd be ions of both of these. So if we look at this beaker here of this strong acid, notice all of the molecules here are completely dissociated. All you see in this picture is a beaker of positive and negative ions. All right, so you don't see any of the original acid still together here because it dissociates 100% into the ions for any strong acid or base. Weak acids and bases dissociate only slightly in water. So what that means is the weak acid or base will turn into ions, but you'll still have some of the original acid or base present. All right, so we say that they dissociate only slightly in water. Their K values are much smaller. All right, so you still have more of the original substance here, if you will. So for example, HF would be in equilibrium with its ions H plus and F minus. But notice it's not a forward arrow here. These weak acids and bases don't go 100% to the products. There's still going to be some HF present, and there's going to be still some H plus and F minus present. So if you're looking at a beaker of a weak acid or base, you have some of the original undissociated compound in there, along with some of the compound that has broken apart into the ions. This is a big idea here. Understanding that strong means complete dissociation in water versus weak is only a slight dissociation in water. So we need to be able to identify certain acids and bases as strong, and then the rest are just going to be weak. And that will play a major part here of how we solve problems with these acids or bases, depending on whether they're strong or weak. So I would make sure you totally understand the difference between a strong and a weak acid or base. On this slide, I'm showing you the 6 strong acids that you need to know and the 5 strong bases. All right, so HCl, HBr, HI, HNO3 nitric acid, H2SO4 sulfuric acid, and HClO4 perchloric acid here. These are the 6 strong acids. You need to have them memorized. You need to be able to recognize them. If you have a problem with one of these acids in it, you need to know they're a strong acid. They're going to dissociate 100%. And then these are the 5 strong bases. All right, they all have OH in them. So lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, and strontium hydroxide. Same thing. You need to know that these are the 5 strong bases, and you need to be able to recognize them, and you need to know that they're going to dissociate 100% in water. They're going to turn into their ions 100%. Just be careful here. Again, don't confuse strength, which is talking about how much dissociation takes place, versus concentration. All right, I can have a higher concentration of a weak acid. All right, that doesn't mean it's now strong. All right, strong acids and bases just mean they dissociate 100%. Concentration is just talking about the moles per liter here that you're forming for each of these. So definitely memorize the 6 strong acids, be on the lookout for them. Same thing for the 5 strong bases. This scenario will hopefully help you understand the difference between a strong and a weak acid here. So if we have 2 separate beakers here, the one on the left has a strong acid in it, so one of those strong acids, and the one on the right has a weak acid in it, okay? So if we add the same amount of magnesium to each of them, right? So we're adding a piece of magnesium to each, same amount, and the concentration of each of these are the same. Remember, strength is not the same thing as concentration. So let's say both of these are 1 molar solutions of the strong acid and 1 molar solution of the weak acid. Both of them will produce the same amount of H2 gas, all right? They both will produce the exact same amount of H2 gas, but the strong acid will do it faster and with more bubbles because it's more ionized. So you need to think about this. In the strong acid beaker, that acid is completely ionized into its ions. So as soon as you add the magnesium, those ions are available and ready to react. So the reaction happens much faster with more bubbles. But it's still going to form the same amount of overall H2 gas here. All right, so when you add the magnesium to the weak acid, it's not 100% ionized. So you have some of the original weak acid together and some of the ions present here. So the ions that are available can start reacting with this magnesium. It's just that it's not 100% ionized, so it can't react as fast with as many bubbles. Over time, it will all react and will still form the same amount of hydrogen gas, but it's just going to do it slower. All right, so make sure you really understand this idea here. Right? They both have the exact same concentration. All right, there's a difference between strength and concentration here. Strong acids are 100% ionized. Weak acids are going to be partially ionized here. So you definitely need to know the list of strong acids and strong bases. Realize that anything that's not on the list of strong, we would just consider then to be weak. All right, so you really just need to know the strong, and then everything else is weak. But I would spend some time here and make sure you understand this idea of what's happening in each of these beakers, the difference between a strong and a weak. Let's look at 2 examples here. So the first one says, if we have 1.25 moles of HCl in water, how many moles of H plus and Cl minus will there be? All right, so the first thing you need to recognize here is, okay, HCl, that is a strong acid. So if it's a strong acid, that means it's going to ionize 100% in water. All right, so if you think about HCl, all right, ionizing and breaking down into its ions, dissociating, you're going to get H plus and Cl minus. And the ratio here is 1 to 1. So for every one of the compound, there's 1 H plus. For every one of the compound, there's 1 Cl minus. So if you know how many moles of HCl you have, you know the exact amount of H plus and Cl minus you have because it's a strong acid and it ionizes 100%. All right, so therefore, the moles of H plus is going to be 1.25 moles. It's exactly the same because it's 1 to 1. And the moles of Cl minus is also 1.25 moles. I told you this idea of having a strong acid or a weak acid in a problem is going to change the problems a little bit. So when you have one of these strong acids in a problem, as long as the ratio is 1 to 1, if you know the moles or you know the concentration of the strong acid, you now know the moles or the concentration of the ions here because it's going to dissociate 100%. If we look at the second example here, this time if we have 0.236 molar HNO3, what is the concentration of each of the ions? Again, nitric acid is one of the strong acids, so it dissociates 100% into the ions. So if you know the concentration of the original HNO3, it's 1 to 1, so the concentration of the H plus would be the exact same thing, and the concentration of the NO3 minus would also be the exact same thing as the original because it's a strong acid and it dissociates 100%. Understanding this idea for these strong acids or bases is very important. Something else to consider here is that the stronger the acid, the weaker the conjugate base is going to be. All right, and then the stronger the base, the weaker the conjugate acid will be. So if we look at this example here, HCl we know is a strong acid. All right, so the conjugate base of that, when we lose that H plus, would be Cl minus. So Cl minus is a weaker conjugate base here. All right, just because you have a weak base doesn't mean the conjugate's automatically going to be a strong. It just means that it's stronger, essentially. So just be careful with that idea. But the key here is, the stronger the acid or base, the weaker the conjugate is going to be. Notice for this one, the conjugate base here, the Cl minus, doesn't want to grab that H plus. All right, this conjugate base is much weaker. It doesn't grab the H plus and reform the HCl. And the reason it doesn't do that is because the HCl is strong, so when you form the conjugate, it's going to be much weaker here. So just be aware of this idea, all right? It definitely can be helpful to understand this in certain situations. Another important idea here to consider is that when you have these acid-base reactions in equilibrium, all right, the position of the equilibrium will favor the transfer of the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. What does this all mean? Weaker acids and bases are favored at equilibrium. So this is a major idea, and typically this appears on the AP exam in some way, usually every year here. All right, and they have different ways that you have to use this. All right, you might not just realize just by looking at, an example that this is the idea that needs to be used, but you have to understand this concept and be able to apply it here in different situations. So if you have an equilibrium reaction with an acid or a base, all right, the equilibrium is going to favor the weaker acids or bases here. So maybe you even have to look at, an equilibrium constant, and based on that information, determine which is strong or weak. All right, but this is the big takeaway. All right, weaker acids and bases are favored at equilibrium. Let's look at how we can use this idea in an example. It says, based on the reaction given below, which substance is the strongest base in this system? And you're given this equilibrium reaction, and they give you the KEQ here. All right, so you need to realize, okay, this is an acid-base system here at equilibrium. Well, according to the idea, weaker acids and bases are favored at equilibrium. Okay, so this is where you need to analyze the KEQ data. According to KEQ, it's 23.8. All right, so remember, KEQ is products over reactants. So if you have a number that is greater than 1, you must have more products. All right, so according to the KEQ, there's more products here. Well, what we know here is that the weaker acids and bases are favored at equilibrium. So if the products are favored according to KQ, that must mean the weaker acid and base are on the product side. Okay? Well, this question says, which substance is the strongest base? So if the product side is favored and the weaker are favored at equilibrium, that must mean the strong is coming from the reactant side or the left side here. But we want the strongest base. So you just need to analyze each of these substances and say, okay, according to the reaction, which one is the base? Well, remember the base will pick up the H plus. So if you notice the CO3 2 minus here is going to the HCO3 minus on the right, so it's picking up the H plus. So the strongest base in this system is going to be the CO3 2 minus. So you can see here how they don't explicitly come out and say, use the weaker acid and base idea that is favored at equilibrium. No, you have to kind of look at this, look at the KEQ and understand that that's the concept you need to apply here. All right, but definitely understand that weaker acids and bases are favored at equilibrium. Be able to look at KEQ data and give what they're looking for to solve the problem. I now want to look at some factors that affect the strength here of an acid or base. Something very important to realize is that not every molecule that has an H is an acid, and not every molecule that has an OH is a base. All right, so that's something very important to understand here. Sometimes you have these really strong bonds, maybe a strong bond between an element and hydrogen, and it doesn't want to break to give off that H plus to allow essentially that H plus to be given off, making it an acid. All right. So if you have high bond polarity, essentially hydrogen is bonded to a very electronegative atom. This tends to increase the acidity of the hydrogen atom because the hydrogen wants to get away. All right. If you have a very electronegative atom here, it's kind of hogging all the electrons. So it makes sense that the H plus is just going to come off, allowing that substance to be acidic here. So for example, you can see here this dimethyl ether. All right, there's a lot of hydrogens here, but this is not acidic. None of these hydrogens really wants to break off and get away in order to make this substance be acidic. It has hydrogen atoms, but just having hydrogen atoms doesn't make something acidic. If we had a very high polarity here, this polarity difference between carbon and hydrogen is not that great. But if you did see a bond that has a high polarity, the hydrogen is more likely to want to break off, allowing that substance to be an acid. Think about HCl. Cl is very electronegative. The hydrogen comes off very easily, allowing HCl to be an acid here. All right, so pay attention to this first factor. Understanding that polarity can lead to a hydrogen kind of breaking off, allowing a substance to be acidic. A couple other things to consider here regarding these factors that affect strength. If you have molecules in this general form, they have an H attached to an O, and then that O is attached to some element here. If that element has a high electronegativity, the H is going to tend to want to come off, allowing the substance to be acidic here. All right. If the X in this case, the element that this O and this H are attached to, has a low electronegativity, typically the OH tends to come off, allowing the compound to be basic. All right, so think about something like NaOH. Na is not very electronegative, so the OH comes off, allowing NaOH to be basic. All right, so just keep that idea in mind here. Also, anytime you have more oxygens around a particular element, the more acidic it gets. All right, so if we look at, for example, HOCl, hypochlorous acid, all right, it's an acid, but it's not too acidic. As we add oxygens around the chlorine, notice what happens. We get more and more acidic here. 2 oxygens around the chlorine is a little bit more acidic than just 1. 3 is even more acidic. And by the time you get to 4 oxygens around the chlorine, you now have perchloric acid, which is a strong acid here. All right, so these are just some things that can affect the strength here of an acid or base. Remember, anytime you have more oxygens around a particular element, the more acidic it's going to be. The last thing I want to talk about in this video is the autoionization of water. Basically, water can be in equilibrium with its ions. So water can kind of dissociate into H plus and OH minus. This is very important because it allows water to act as an acid or a base here. So if this is in equilibrium, we can kind of write a K for this. We call this KW because it's for water. All right. With water would be a pure liquid, so it wouldn't participate in the equilibrium. So Kw would be equal to the concentration of the H plus times the concentration of the OH minus here, our products, and they're not going to be over any reactants because this would be a pure liquid water which doesn't participate in the equilibrium. The value of Kw at 25 degrees Celsius is 1 times 10 to the minus 14. All right, so essentially if you plug in Kw, we know that the concentration of H plus times the concentration of OH minus would be equal to 1 times 10 to the minus 14th here. The AP equation sheet gives you this Kw. It also gives you the value here. You might need to use this idea of Kw in problems. So just be aware of this and understand that the value here of Kw at 25 degrees Celsius is 1 times 10 to the minus 14th. Again, water is able to kind of ionize here, and we can write an equilibrium for that, which we just call Kw.